So in today's discussion session, which will we will resume our discussions on the structure of relativistic quantum mechanics, and for today we were going to deal with the one set of differential equations which we had found to be compatible with special relativity, which goes by the name of the Klein-Gordon equation. So remember, we were trying to find out replacement of the Schrodinger equation, which was first order in time but double derivatives in the spatial derivatives, and that was not Lorentz invariant or covariant, and therefore we were after some equation which manifestly its Lorentz covariant structure, and we ended up getting one potential equation being the Klein-Gordon equation, where the D-Alembertian, which is the double derivative with respect to time and double derivative with respect to the spaces, they hit upon the wave function psi. So that is called the Klein-Gordon equation, and in today's discussion we will be discussing about the salient properties of the Klein-Gordon equation. All right. So the relativistic consistent Klein-Gordon equation, when it is written in the partial derivative forms in Cartesian coordinate, can be written as -1 upon c square double derivative with respect to time plus double derivative with respect to x, y, and z, hitting together the wave function psi with a minus h naught square, which is being multiplied from the left hand side, should be equal to some invariant quantity times the wave function. Why invariant quantity? We have written m square, which was an invariant. Remember, p mu was supposed to be m square, which was an invariant quantity because of its scalar nature, rank 0, 0 tensor. P mu was supposed to be minus m square c square. So this was the invariant quantity which is appearing over here. Why do we want some invariant quantity on the right hand side? Because left hand side, this box operator, we have learned in the discussions on special relativity that it has an invariant structure. Box is a Lorentz invariant operator. So therefore some invariant object, which is operator, hits the wave function psi, and as an output of that we should find out something which is also invariant times hitting the wave function psi. So this is a Lorentz invariant equation for the wave function psi. Now looking at the structure of this differential equation, where the double derivatives with respect to time x, y, and z have appeared separately, there are no mixed derivative like del t del x or del x del y. And also the coefficients of all these double derivatives are constants. 1 over c square over here, 1 over here, 1 over here, and 1 over here. There is no coefficient which is a function of x, y, z, or t. In that case, where all the derivatives are separate and all the coefficients of the derivatives are also constants, we can employ something called a method of separation of variables, that I can think of that the wave function which we are after is a separable function of individual variables t, x, y, z. So we thought of a wave function which has x dependency, y dependency, z dependency, and time dependency captured as a separate product functions tt, xx, yy, zz. So this we are looking for a basis of this equation. So this is a potential solution which can satisfy this equation. And if we are familiar with the method of separation of variables in various differential equation courses or mathematical method courses, or even in electrodynamics, you might have come across to exact same equations. Then if I feed up this equation into the differential equation, what we get would be the double derivative of time will only see the first function capital T, because there is no other time dependency anywhere else. The double derivative with respect to x will only see the capital X function, because there is no small x dependency anywhere else in the function. And similarly for double derivative with respect to y, which will see this capital Y function, and double derivative with respect to z, which will see the capital Z function which we have. So these are individually different functions of different variables, and different derivatives will hit upon different individual functions. So once I do that I feed this psi into the differential equation, and the double derivatives have acted upon, then what I can do, I can divide the whole sides with the wave function psi itself. After the double derivative has acted upon, then I will divide both sides by psi. So right hand side will become a constant, which is m minus m square c square. Left hand side, you will get a structure like minus h square 1 upon c square t double primed upon t plus x double primed upon x plus y double primed upon y plus z double primed upon z. That should be equal to minus m square c square. Now once we have this structure, what we can do is to take first this minus h square on the right hand side. So if I take minus h square on the right hand side, left hand side will be not having the h square, and h square will come downwards without flipping the sign on the term on the right hand side. Then next what we can do is to take the three spatial derivatives x double primed, y double primed and z double primed terms on the right hand side. So I take these to this side. Okay, so that would make the differential equation like, so suppose I take all these terms from here and move it on the right hand side. So they will move to the right hand side with a negative sign. That means I will get 1 upon c square. Actually it should have been minus 1 upon c square because the time derivative comes with a minus sign. Minus 1 upon c square t double primed upon t should be equal to plus m square c square upon h square minus the double derivatives of x divided by x, double derivative of y divided by y, and double derivative of z divided by z. So I would have this kind of structure. So you see left hand side is only a function of t, while right hand side is a function of x, y, z, all these three functions. Actually, what we can do that since this depends on a function only t, the double derivative is also a function of t, small t, and the function itself is a function of t. So left hand side is only a function of t, some function of t, and right hand side is some other function of x, y, z, which are coming from this capital X, capital Y, capital Z. So if that is true, this can only happen if two functions which are functions of two different independent variables, they should agree to each other at all x, y, z and t. That is our demand. We are not looking for what x, what y, what z this differential equation is satisfied. We are demanding some functions which satisfy the differential equation at all time and spaces. So that means this equality which we have just landed up should be true at all t, x, y, z. So that means they should better agree to a particular constant. Okay, so let us call this constant as a minus e square. Okay, so minus 1 upon or plus e square we can call it. Minus 1 upon c square t double primed upon t should be equal to this combination, which is m square c square h square minus the double derivatives of x upon x, double derivative of y upon y, plus double derivative of z upon z. That should be equal to e square, let us say, some constant e square. Once that has happened, again the same thing can be played on the right hand side equality, meaning this function together should also be equal to the same e square. So then what I can do, I can take this m square c square and this double derivative with respect to y and z towards the right hand side, and I will get an equation like x double primed upon x is equal to e square minus m square c square upon h square plus y double primed upon y plus z double primed upon z. Okay, so therefore again left hand side is a function of small x, right hand side is a function of y and z, and they should agree on all x, y, z point. That means they should better agree to that they are equal to some constant. So x double primed upon x is equal to some constant, let us call it minus kx square. So I will get capital X double primed upon x is minus kx square. Similar game I will play on the remaining quantity y double primed upon y and z double primed upon z. So since this combination is equal to another constant which is minus kx square, again I can take this z double primed and this quantity on the right hand side. So y double primed upon y should be equal to minus some constant which is minus ky square. and ultimately you play the same game on the z variable itself, and you end up getting that z double primed upon z should also be equal to some constant minus kx kz square. So ultimately the differential structure will break down to 4 pieces, that x double primed upon x should be equal to some constant, y double primed upon y should be some other constant, z double primed upon z should be third constant, and then the temporal part should be equal to some constant which is a function of all the 3 constants which we introduce, kx, ky, kz. Together they determine what E the 1 over c square will. So there should be 1 over c square, which I have missed in this notation. So this 1 over c square times t double primed upon t should agree to. So kx, ky, kz determine this E because they have to satisfy the differential equation. Alright, so these all 4 functions, capital X, capital Y, capital Z and capital T, they do satisfy harmonic oscillator kind of differential equation structure. Okay, so therefore their solutions would be oscillatory exponential integrals. So capital X will be some function of plus minus iota kx times x, y will be e to the power plus minus iota ky times y, z will be e to the power plus minus iota kz times z, and similarly the temporal part would be e to the power plus minus iota e upon e by t. So these are the 4 functions which would be making up the psi which satisfies the Klein-Gordon equation. Okay, once I combine, that means I put all the functions together, I can write down the wave functions as product of all function, which will become e to the power either plus iota kx minus iota ky plus iota kz, or any combination of this plus minus. So any combination of kx, ky, kz with plus or minus sign, I'm going to call some vector k. The vector k's component along x, y, z will be decided upon what constant you have chosen for kx, what constant you have chosen for ky, and what constant you have chosen for kz. So any constant or any signature, together they will generate some spatial vector k. So all the sign differences which are appearing differently, I'm saying that can be captured by some k. Okay. However, for the temporal part, I'm going to write it explicitly. There are 2 possibilities of the temporal part, one with plus iota IET and another is minus iota IET, which I write separately. First function will be some k times e to the power minus iota ET, and the second set of solution would be e to the power plus iota IET and minus ik dot r. So in these 2, spatial vectors capture the signs of a spatial part, but explicitly I have written e and minus e because there is no temporal vector I could have written like, but that is how I have decomposed it. The upper thing is called positive energy solution because the energy is typically measured by operation of Hamiltonian, which is effectively minus iota h bar, plus iota h bar times del del t times psi. If I take the first wave function, this operation gives me a positive e times psi back. So therefore, in the exponential, if I have a minus iota et, then it is a positive energy eigenfunction. However, when I apply to the second one with a exponential with a positive argument in the exponential, then the Hamiltonian operation IH del del t upon psi for a stationary solution, I will get a minus E psi. So this is what the definition of the stationarity, even in Schrodinger equation we demanded that this should be the definition of stationarity, which remains true in the case of Klein-Gordon equation as well. So therefore I will have these 2 solutions possible, one with positive E and one with a negative E. Contrasted to the Schrodinger equation, there only we had one solution with positive E. Iota h bar del del t psi was h psi, and that was supposed to be E psi. Only one signature was there. Here in the relativistic setting, there are 2 signs which are possible, positive energy and negative energy. And in general, any relativistically valid wave packet can be made from these solutions superposed with different coefficients. So I will integrate over all k. So all vectors in the space can be integrated over all plus minus sign or their value of the constant will be captured by variation of d3k. d3k contains all possible e to the power ik dot x. and they come up with different weight factors. And e to the power minus IET, I'm not summing over integrating over e as well, because when I change kx, ky, kz, e automatically changes. The e is not an independent function, independent variable. It is just a function of kx, ky, kz. So in this process, when I have integrated over all kx, ky, kz, I have effectively integrated over all possible energies as well. And if I want a relativistic real wave function, I can multiply complex, or I can add a complex conjugate to that as well. Okay. So now, once we have a solution of all the components of the wave equation, the invariant wave equation, we can try to see what kind of structure emerges out of it. So we had this equation at hand where the double derivative of time, double derivative with x, double derivative with y, and double derivative with z. We are hitting the wave function and ultimately giving you a minus m square c square of psi. Now one can see that this equation can be converted in terms of some meaningful operators which we are familiar with. And what are those? So first of all, we have demanded that the wave function which we are looking for can be separated in x, y, z and t as well. So therefore, we can think of looking at this equation which is present over here in some sense as the manifestation of the invariant equation p mu is equal to m square c square. Remember, in special relativity, we learned that p mu is supposed to be minus m square c square. Okay, this is invariant, and this, because of its contraction, this upper index, lower index repeated and summed over, we know that this is also invariant quantity. So now we can see that this object and these objects are invariant objects, and if I convert things into the components, let us say it had a component p0 which can be written as minus e square c square, if you recall. Then the remaining three spatial p1, p2, p3, which will appear as p square, as we have seen over here. So ultimately what we have is minus e square upon c square hitting the psi plus vector p square operator now this time is equal to, hitting on psi, is equal to minus m square c square psi, which is the manifestation of the operatorization of this invariant equation. Okay, now we know in quantum mechanics, px operator is the spatial derivative of wave function with a minus iota h bar factor. Similarly for y, py will be minus iota h bar factor times the del del operator. And similarly for z as well. So z operator is also del del z operator with minus iota h bar factor. Now remaining over here, for stationary states, we know the energy which appears is also the temporal derivative which hits the psi. The Hamiltonian for the stationary states, it so happens that h of psi, which is for stationary state e times psi, can be represented as the temporal derivative of time. So therefore, whatever elements appearing here or whatever operators appearing here, they can be converted into differential operators. Okay. So I have two of p's appearing here, spatial px square. So spatial px square will be written as px times px, and I know px operator is this, and 2 times px hitting the psi will be equivalent to minus h square partial derivative hitting twice the wave function psi. And similarly for py will be minus h square del 2 square upon del y square hitting the psi. Pz square will be del minus h square del 2 z square hitting the psi. Lastly, we have the energy thing, which e square c square was appearing. We know now that energy has also to be written as minus plus iota h bar this time, d psi upon dt, and therefore the e square will be, this quantity hitting twice will be just e square psi. You can verify that I have written iota h bar del t twice, and iota h bar del t itself is equivalent to Hamiltonian, so it is h psi, and this operator, this becomes a new wave function psi prime, eigen wave function, let us say e psi. E will come out, and the second derivative operator will hit, the Hamiltonian will hit, and again another e will be popped out, so e square upon psi. So ultimately the invariant equation, which was minus e square c square psi plus all the spatial derivative px square, py square, pz square psi minus del minus m square c square psi. So whatever we had as a invariant equation in temporal derivatives, spatial derivatives can be converted into respective operators with e replacing the temporal derivative and spatial derivatives being replaced by the p operators. So that is another manifestation of writing the quantum operator in the relativistic regime. Okay, so this is an equation which one should be solving for relativistic particle. This is a good replacement of a Schrodinger equation, so to say. Let us see this through an example. Again, we are all familiar with the step problem or the well, quantum well problem, where there is a quantum well and a particle is supposed to live in that well, and we want to know what is the probability of the wave function being in the regime 2 or regime 1 depending upon the depth of the potential well. So again, we set up the same problem. There is a potential well which goes up to the depth of minus v naught between 0 to r naught and is 0 afterwards. So this is the usual step problem. Only thing is that this time we will not solve this equation through Schrodinger equation, but we will try to solve it using the relativistic equation which we have, which is over here. All right. So the thing we should worry about, we should be careful about, is there are two regimes, region 1, region 2. In both the regimes, quantum equations has to be solved while potential remains constant in both the regimes, but not at the same value. In this regime, it is value 0. In this regime, it is value minus v naught. So if I go to regime 1 first, in regime 1, you can see it is the energy of the particle, total energy of the particle will be increased by E plus V naught. It becomes a constant shift will add to the energies equation if you write down. So therefore the free energy of the particle or the P0 part of the momenta should be treated as E minus V. It so happens that V is already negative of minus V naught. So it will ultimately will become E plus V naught upon C. So it is almost like a free particle in this regime with extra energy supplied to it through a negative potential. So its zeroth component of momenta will become E plus V naught or equivalently E minus V. E minus V is equivalent to E plus V naught divided by C and usual the 3 momentum P. And they have to satisfy the same wave equation P mu is equal to minus m square C square, the equation which we have written over here. This is the relativistic description. So let us open it up. Write it down. Zeroth component is this. All the spatial component in this equation come with negative sign, so they can be taken on the right hand side of the equation. Okay. So that is what we do. So just a second. Yeah. So that is what we can do. Actually, in this equation, if I write down, there was a overall minus sign over here. If I flip the minus sign, this should come with a positive sign. So let me fix it first. This should be a positive sign over here. And therefore, the equation which we are looking for, P mu is equal to plus, depending upon which we write. If we write E0 with a minus sign, P0 with a minus sign, then it remains a minus sign here. If I write a plus sign here, which is like this, then it should appear as a plus sign over here, which is good. So therefore, I took all the P operator, the square of P operator to the right hand side. It added to the m square C square already present over there. And left hand side would be left with P0 only. And in the region 1, P0 is E minus V. So therefore, the equation which I have to solve is E minus V whole square divided by C square is P square plus P square C square plus m square C4. This is the effective momenta energy relation for region 1. We can call this quantity E minus V as E tilde, and that is a free particle with energy E tilde equation. E tilde square divided by C square is equal to the P square C square plus the P square C square, the spatial P square C square plus the mass of the particle. So as we discussed in the region 1, the energy is shifted to E tilde. Okay. So if I write down the Klein-Gordon equation which we had initially started with, ultimately it is a wave equation. The temporal derivative and the spatial derivative are appearing. As again, we can write down the wave function into radial part, just like we had previously decomposed into x, y, z, we can decompose it into radial, angular part as well. So write down the Laplacian, the spatial Laplacian which is appearing over here into the spherical polar coordinate system. I know that becomes double derivative with respect to r in a particular way, double derivative of theta in a particular way, and double derivative with respect to phi in a particular way. And these two quantities can be clubbed as a single object, which are all constants, mass and the potential which is appearing over here. Remember, v is minus v naught, so therefore a relative sign difference will appear. Okay, so for region 1, which is r less than r naught, it will be v naught. For region 2, which is r greater than r naught, v naught will vanish. So both the equations, these equations are almost the same. Only thing is that v naught is present here with an overall positive sign or not, depending upon which region you are in. So we can look for the stationary state solutions, which is some psi of RT, which is dependent on spatial distribution, which we have to figure out. But temporal distribution, I say that it is in the stationary state, that means e to the power minus IET upon h bar. This is eigenstate of del T operator. If that is true, the derivative, temporal derivatives appearing here and here will just throw up e tilde squares. So that will become this times the phi. All the spatial derivative will hit phi as r derivative, theta derivative, and phi derivative, and we have to figure out what their character is. But temporal derivative will hit and bring down e square over here. So that is what we have done. Okay, in region 1, e tilde is e plus v naught. In region 2, e tilde is e. That's all what we have to be careful about. Okay, now you can see that if you have solved hydrogen atom problem or any spherical symmetric problem, the theta pi phi part, angular part of this differential equation is to be easily solved, because in the potential there is no theta pi dependence. So therefore angular part is already known to us, and they are the angular parts eigenstates are ylm theta phi, the spherical harmonics. So I urge you to refresh your analysis of spherical polar coordinate systems and Laplacian over there by looking at 3D oscillator, harmonic oscillator, or hydrogen atom, or any spherically symmetric problem like this one. You will realize, since this is spherically symmetric problem, you should expect eigenstates of angular coordinates, angular differential operators, and ylm theta phi are those. So therefore I know my state which I am looking for, phi r, can have a non-trivial structure in the radial direction, but in the angular direction it better be ylm theta phi, provide me a good basis. And they satisfy the Klein-Gordon equations angular component. So I decompose the angular and the radial part like that. Put this unsarge solution into the differential equation which we are after here. There are temporal derivatives, there are angular derivatives here and here, which will hit upon the phi and give me back ylm theta phi, because ylm theta phi are the eigenstates of the angular double derivative operator. And ylm theta phi being hit upon by the angular derivative part come back with the eigenvalue L into L plus 1. All this you might have seen in 3D systems, spherically symmetric potentials, harmonic oscillators, or hydrogen atom. Their L into L plus 1 came about as the eigenvalue of the ylm theta phi operator, or ylm theta phi eigenstate corresponding to the operator of the angular derivatives. So all these angular derivatives are replaced as minus of L into L plus 1 times the ylm theta phi. So all the terms will have a ylm theta phi which I can pull off, and the radial part will be left like this. This is the standard business you have done for the spherically symmetric harmonic, spherically symmetric potential in any case. Only the potential structure has changed. The spatial derivative and the temporal derivative structure has slightly changed, not completely. Only thing is that energy square has appeared, because Schrodinger equation energy was only coming with E. This time E square has appeared. So the K square, which was used to appear previously, had an E minus V structure, if you recall, in the ordinary Schrodinger equation. This time we are talking about a relativistic version. So energy will also appear in the same footing as the other momentum components. They will also appear with a square. So the K tilde square will be E tilde square minus M square C square. Okay, so that you can see I have just clubbed these two things as K tilde square and these two things as L minus into L plus 1 times the radial part. This is also radial into ylm theta. This is also radial to ylm theta. This is also radial into ylm theta. And this part is giving me minus L into L plus 1 times RLM R times ylm theta. So ylm theta phi is a common to everyone. I pull it out, send it towards on the right hand side of 0, and the radial part is left with this equation. I identify the component which was appearing as E and M as a k tilde, which is this. So this becomes a fairly simple differential equation. You might or might not have seen it before. If you have not, this easy step you can follow. You can use another variable u, which is just r up to a multiplication of the k tilde which we have defined over here. The square root of this quantity multiply with r. I go and define u. That is just a method of calling this object as u square. And therefore, all other quantities which are appearing over here can be returned into variable of u. If you do that successfully, this is again a straightforward algebraic exercise, you will realize that the differential equation which we are writing is just the Bessel differential equation in u. So what I did, I just called k tilde r as u, converted every r appearing over here as u, and you will see that this becomes automatically a Bessel differential equation. Since I have written in terms of k tilde, the E tilde has appeared over here. E tilde was E minus V, which is equivalent to E plus V naught in the region 1 and equal to E in the region 2. So that's all. And the Bessel differential equation you might have seen, or if you have not, just look it up. The solutions are the Bessel functions of various kinds. So I am writing in terms of Bessel and Newman functions if you are interested about knowing the nomenclature, but Bessel functions of two kinds, JLs and NLs. If you follow the literature of the Bessel equation, this equation you might have Bessel differential equation you might have solved, for example, in solving the electromagnetic wave equation or the electrostatic potential in cylindrical boundary conditions as well. There the same equation comes about and the same two solutions appear. It so happens that one piece of the solution, which is NL, it diverges at u is equal to 0 at the center. I do not want that. I want my solutions or the wave function to be regular everywhere inside. So therefore, if this term should not appear, that means m tilde should be 0. So all I am left with is the first piece. The radial part should be just the JL k tilde r, where k tilde is this. N tilde is some normalization function which I will put. So overall wave function will become this radial times ylm theta phi. Okay, this is for region 1. For region 2, which is the exterior region, you can do this analysis once more and you can try to see that k tilde will be replaced by k, v naught will vanish to 0, and I have this equation. Again, you can see here I can use identification k naught, which is minus iota times k. That is just a variable substitution, what I am trying to do. Okay, if I do that, the solution in the outside region will again be JLs and NLs. Since I'm talking about outside region, I should not take kr tending to 0, which was supposed to be valid for interior region. So there is no danger of things diverging over here because I'm not supposed to go towards r tending to 0 with this solution. However, these solutions, which are JLs and NLs, can be rewritten in terms of two other Bessel kind of function, which is Hankel function. This is all again differential equation exercise. If you know, you just look it up. Solutions of Bessel's equation. Two linearly independent solutions are JL and NL, and their combinations are also, you can see this is the combination, and the second one is the complex conjugate of that. I can write in terms of JL and N or in terms of HL and HL1 and HL2. This is equivalent to, if a harmonic oscillator solution you are looking at, it can be written as cos and sine or e to the power I omega t to the power minus I omega t. Both of these things can be combined into each other. So equivalently, I can write this, the same thing. I'm not supposed to take r tending to 0. This remains true, but I do not know whether this combination is finite everywhere else or not. And actually it is not, because this becomes very manifest if I write in terms of this variable. Again, the second piece here diverges when r tends to infinity. At infinitely away, my wave function will diverge. Again, that I do not want. So that means coefficient of this should be 0. So n prime should be 0, and I should be left with only n prime with the first Hankel function. That is equivalent to say, if I want R to be completely regular function in the exterior, m should be just iota times n, such that I can give this regular function. Okay, so this is the usual quantum mechanics stuff where you throw up the divergent problematic pieces and constitute your solutions accordingly. So inside I have solutions of JL, outside I have solutions of Hankel function. Only thing you have to be careful about, I have done it in a particular way. For the interior case, I had defined a k tilde which appears in the argument, and exterior region I had defined for iota times k naught. So that appears in the argument, Hankel with iota. This was just a convenient way of realizing the finiteness or infiniteness. If you kept working with KR, you would be working with JLs and NLs with real argument and whatnot. There you will not be able to figure out so cleanly as you do. The physics is the same if you work in any variable. This is easy to realize, visualize, and just a variable transformation. So that is what I am allowed to do. So if you do that, you will get this solution. This is the exterior solution. Again, YL and theta phi will be multiplying to that. And at the boundary from region 1 to region 2, I want things to match very smoothly. So remember the problem which we are looking at. So the potential which we were here. At R0, I do not want things to diverge again. This should have some functional form here, JL functional form, and HL1 functional form here. And they should match here. So I should smoothly go from region 1 to region 2. So the curve should match, wave function should match, its derivative should also match. So these two conditions can be written together as the wave function's radial component should match, YL and theta phi anyway is going to match because we are not doing anything to them that are common to both sides. So radial part should match, and its derivative, prime is the derivative with respect to R. Equivalently, n should, the JL part inside with normalization n tilde, HL part outside with normalization n prime should match, and their derivative should match. What you can do, you can either convert this n primed as n tilde JL divided by HL1 and put it here, and then n tilde on both sides will cancel and you will get this equation. That is just taking care of the normalizations which is appearing. Or you can just simply divide equation number 2 to equation number 1 and you will get this equation. So this is the matching condition which is required. JL primed at the location of matching divided by JL at the location of matching should also match to HL primed divided by HL at the location of matching. And this will give me for different L's, different matching conditions will appear, so that you can smoothly write down a wave function that will, so this matching condition will tell you what values k tilde can supposed to take, whether they come in integer, non-integer kind of steps. So good exercise is to write down what is the matching condition for L is equal to 0. So your exercise is write down what is JL KR0, write down its derivative, take the ratio and put R0, and the similar to that side. You will obtain there is a matching condition for L is equal to 0, which I leave you with an exercise for this discussion session. Okay, so we know how to solve differential equations for a relativistic system in a standard scenario. We have solved this problem for non-relativistic particle already in our quantum mechanics course. Now for relativistic particles, this methodology, the Klein-Gordon equation, should dictate the discourse, and the solutions which we obtain is the Hankel functions and the Bessel functions on the two sides and their matching condition for smooth matching. This replaces the standard matching condition which we have obtained in the usual Schrodinger case potential well problem. So this is the relativistic conditions of the wave function matching. Okay, so I stop over here.